All right, let's get started. Welcome everyone to the SNAPP seminar series. It's a great pleasure today to have Christina Liu presenting in the SNAPP seminar. Christina is actually one of the organizers who started the SNAPP seminar series, and I just learned that she actually came up with the name of this seminar. So she's currently an assistant professor at Cornell University in the School of Operations Research and Information Engineering. Prior to Cornell, she did her postdoc at Microsoft Research, New England. She received her PhD and master's degree in electronic engineering and computer science, both from MIT, and her bachelor in computer science from California Institute of Technology. Her research interests include algorithm design and analysis, high-dimensional statistics, inference over networks, sequential decision-making under uncertainty, online learning, and network causal inference. And she will actually be talking about something related to this today. Without further ado, Christina, I'll let you take it from here.
Great. Thanks so much, Jing, and thanks for the invitation. I'm really excited to tell you about this very recent work. So today I'll be talking about overcoming the long horizon barrier for sample efficient reinforcement learning with latent low-rank structure. And this is joint work with my PhD student, Tyler Sam, and collaborator, Yudong Chen at UW-Madison. So Tyler is actually here on the call. I think Yudong should be joining later as well. So if you have questions, you're welcome to as well type it in the chat, and Tyler and Yudong I think will be happy to answer. But I will also make sure to stop in the middle for questions. So I'm happy to take questions. So. All right, so to get started, I just want to introduce the context of the Markov decision process that we'll be considering today. Here we have a decision-making agent that's interacting with the unknown environment. The agent observes an initial state, x1, and responds by taking an action, a1. In response to the state and the current state and the action that was taken, the environment then returns a reward and transitions to a new state, x2. This new state then is observed by the agent. The agent then again responds by taking an action, and the environment again responds with a reward and transitions to a new state. So the agent and interacts with the environment in this repeated in this back and forth manner over a horizon of length h, and the agent wants to find a policy or a way of choosing actions as a function of the states that maximizes its total reward that's collected across this length of the horizon. So of course, when the reward function and the dynamics are actually known, you can compute the optimal policy via dynamic programming. It could be costly, but it could be done. And today we're going to consider the reinforcement learning setting when the reward and dynamics are unknown. And the goal is going to be to find a near optimal policy using samples from a generative model when this reward and dynamics are unknown. And here you should think of the generative model as the algorithm having access to some black box that can query by inputting a state and action pair and observing the reward or the additional transition that the new state that the system transitions to. So there's a lot of applications that can be formulated in an MDP. There's been a lot of recent empirical success in reinforcement learning that's been shown for game playing and robotics in particular. These are settings in which you do have often access to a good simulator, and the results often rely on having an immense amount of data and computation. Listed below, I've also included many operational applications that also have a sequential decision-making framework. And these are settings in which the size of the state and action space can be very large, potentially because of combinatorial structure. Yet these are systems that we actually do know a lot about. So they are clearly structured. And there's been a lot of research in this community, even studying each one of these application domains. And from all of this rich research, there's many good heuristics that have come out of it that have been designed from simple models that are optimal on the simple models, but yet can still be deployed on more complex models. And whereas even though we don't know what's exactly optimal for the more complex models, these simple heuristics actually still perform really good in practice. And the reinforcement learning algorithms actually struggle to beat the heuristics because the reinforcement learning algorithms are kind of so general and such a general framework that they're not able to exploit the structure that we actually know exists in many of these problem domains. So a central research question that arises is, how do we actually design reinforcement learning algorithms that can provably and efficiently exploit structure arising in real-world systems? And this will, of course, depend a lot on the application domain. The application domain will inform what kinds of structure are actually reasonable and common in this application, what kind of information is commonly available. And as a combination of the type of structure and the available information, it leads to an interesting research question of how do we actually exploit this structure and information to lead to efficient reinforcement learning algorithms. And today we're going to specifically look at exploiting low-rank structure in reinforcement learning, but I'm very interested in this broader research direction. So if you have interesting applications where you have thoughts about what are meaningful structures and available information to look at that it would be impactful to design reinforcement learning algorithms for, I would be very happy to hear your ideas and suggestions. All right, so let me actually dive into the model and introduce some notation. We're going to be considering a finite horizon reinforcement learning setting where you have an agent that's interacting with an unknown Markov decision process over a horizon of length h. And we're going to use pi to denote the policy of the agent. The policy is a function that maps from the states to an action and is also indexed by the step h within the horizon. And the parameters of the MDP model will be described by the reward function, which is a function mapping from the state and action pair to a bounded reward between 0 and 1. And it's also, and the other parameter of importance is a transition kernel, th, which is again also indexed by the step h and maps from a state action pair to a distribution over the next state. Next, I'm going to define two functions that are important for kind of setting up the objectives and the algorithm. The first is a value function. The value function at step h at state x using for policy pi is defined as the expected cumulative reward that the agent would collect if it were to play policy pi starting from step h at state x. And the Q function, which is also called the action value function, is just a one-step deviation from the value function. It's the reward that you collect, the agent would collect from playing action A at this current step H at state X, and then subsequently for all remaining steps until the end of the horizon following policy pi. So the only difference between the Q function and the value function is that the Q function is kind of allowing the agent to deviate from this policy pi at this first step and then playing policy pi for all remaining steps. And it's capturing, again, the expected reward, the expected cumulative reward. And the goal of the agent is to find a policy pi that maximizes the expected total reward. So we're going to denote the optimal policy with pi star. The optimal policy pi star and the associated value function in fact satisfy the following Bellman optimality conditions: that the value function at the end of the horizon after after step H is 0 because there's no further reward to be collected. And then the Q function at step H for the optimal policy is the reward function plus the expected value that the agent would collect from playing the optimal policy from step H plus 1 to the end of the horizon. And given the Q function at the optimal Q function at step H, you can compute the optimal value function and the optimal policy by simply maximizing over the actions. So I've written the equations kind of suggestively. You can see directly that optimal policy can be computed via dynamic programming. And I guess I've put the simple pseudocode here. You would first start with you do backward recursion starting from the end of the horizon with the value function being 0 for all states. And then you, given the value function at the next step h plus 1, you can compute the q function at step h, and it give, using the definition, and then the value function at step h and the optimal policy at step h can both be computed from the q function at step h. And you just then recurse backwards from the end of the horizon all the way to the beginning of the horizon. So if I don't know so you can see, where do I use the knowledge of the model? I'm using it to compute this step in the middle, to compute Q star. So I'm using it to, assuming knowledge of the reward function, and I'm assuming knowledge of the transition kernel to compute this expectation here. So the idea of empirical dynamic programming is pretty straightforward. You simply replace the reward function and this expectation with empirical samples instead. So this particular, I guess, instantiation of empirical dynamic programming is called empirical value iteration, because we're iterating on this estimate of the value function we had with one-step updates. So we can ask, what's the sample complexity of running empirical value iteration? First of all, I'm going to define what our goal is. Our goal is to find an epsilon-optimal policy. So a policy pi and its associated estimate for the Q function Q are epsilon-optimal if for all states, actions, and steps H in the horizon, the value function of this policy pi is within epsilon of the optimal value function. And this estimate for the Q function Q is also within epsilon of the optimal. And so because the empirical dynamic programming approach needs to sample from every state action pair to construct the estimate for the Q function, the optimal sample complexity is going to scale with S times A. In particular, the optimal sample complexity defined an epsilon optimal policy is S times A times H cubed, so the horizon cubed, over epsilon squared. And now the critical question for the talk today is to ask, if we impose additional structure on the MDP, can we reduce the sample complexity, in particular with respect to the scaling on the dependence on the size of the state in action space? So in particular, if we impose low rank structure on this Q function, so what low rank structure means is that this Q function, when I review it as a matrix, can be decomposed as a product of a tall matrix and a fat matrix. So because you can see that this low rank assumption actually reduces the degrees of freedom of this matrix from S times A to S plus A. And so the goal or the hope is that if we knew that such a low rank structure did exist, could we instead just sample from only order S plus A state action pairs and then use matrix estimation to construct the estimate of our Q function for the remaining state action pairs? So we weren't the first ones to think about this problem. Xia, Sang, Xu, and Yang showed in 2020 that, in fact, there is a simple and efficient algorithm which gets a sample complexity of S plus A as desired over epsilon squared. So that sounds really great. But the one limitation is that their result actually requires bounded horizon. So in particular, for example, like this sample complexity result is only valid if the horizon is less than some constant, for example, 20. And so the starting place of this work was this question of whether this bounded horizon constraint was truly fundamental or not. And I did want to mention as well that there is actually empirical evidence that there's in simple problems of in OpenAI Gym and stochastic control, where these two groups, Yang et al. And Rosada, have shown that these problems do exhibit approximately low rank structure, and empirically using low rank methods seems to help performance. Okay, so to I guess start solving a piece of this puzzle, I want to first give you a simple illustration. Suppose I have a very simple setting where I have two states and two actions. And we assume that this optimal Q function is rank 1 for all steps H. And we want to evaluate the value of a policy pi. So a natural algorithm would be to just say use backward recursion, where suppose I was given an estimate for the value function at the last times step. I just use backward recursion for to estimate a subset of these entries. In particular, because it's a 2x2 matrix and it's rank 1, we need to estimate at least 3 entries. And given these 3 entries, we're going to use least squares and the low rank assumption to estimate the fourth entry. So to visualize it, suppose I'm given a value function, an estimate for the value function at the terminal step of the horizon H. I will use a backward recursion to estimate the 3 entries in red. And here, actually, I want to comment that I'm going to assume for the purpose of this illustration that in the backward recursion step, we actually do have knowledge of the true transition kernel. So this is a true expectation and the reward function. And then we're going to use least squares to just estimate the last 4th component. And then we can repeat this. So then given the estimate for the Q function at step H minus 1, we can estimate, get an estimate for the value function at H minus 1. And then given the value function of H minus 1, we again use backward recursion to estimate the 3 entries in red and use least squares to estimate the 4th entry in blue. And repeat this all the way until the beginning of the horizon. So this is is the kind of the most simplest setting because it's only a 2x2 matrix with rank 1, but it's also a very natural algorithm to consider. So interestingly, we're actually able to show that there exists an MDP in the above setting that has with horizon H and an optimal policy pi, for which if the terminal estimate has an error of epsilon, then for sufficiently large horizon H, policy evaluation using the above algorithm results in an error for your value function estimate to grow doubly exponentially in the horizon. So that sounds pretty unfortunate. It does suggest that perhaps only assuming that the optimal Q function is low rank is too weak. And it does seem to support the bounded horizon constraint in Shah et al.'s work. And how we show this is to construct an example such that the error in the estimate of the value function satisfies the following recursion for an optimal policy pi. And the recursion is that the kind of error grows accordingly to this recursion where there's a linear term plus a quadratic term. And this quadratic term is the term that contributes to this doubly exponential growth of the error. And this quadratic term does arise from the nonlinearity in the estimate of the Q function that comes from the matrix estimation step. So in particular, when you have a 2x2 matrix, you observe 3 entries and you want to predict the 4th one. This is the explicit least square solution to the matrix estimation kind of step. It's the unique rank 1 completion of the matrix, and it does align with the algorithm that's actually used in Shah et al.'s paper. And particular, this estimate for the entry 2, is the ratio between the product of the off-diagonal entries divided by the other diagonal entry in 1, and it's this quadratic term that ends up contributing to this doubly exponential growth of the error. And in Shah et al.'s work, they assume a small discount factor, which imposes an effectively bounded horizon to ensure that this error does not amplify. So any questions maybe up to this point on the framing?
I have a question about the model.
Yes.
So it's clear in your theorem, but more generally, when you say low rank structure, are you assuming that the rank is same for all H?
We're going to assume that the bound on the rank is the same for all H, but it doesn't have to be exactly the same for all H.
Okay. Okay.
But they all have to be kind of bounded by.
Okay. And the empirical work that you pointed out essentially notes this in the OpenAI gym examples and so on, I guess. Right?
Yeah, I mean, so I have to comment that it's a little bit, it's weak in the sense of they look at they try to, in order to verify approximate low rank, what they do is they solve as best as possible for the optimal Q function, and then they plot the spectrum, and they show that the spectrum kind of drops quickly. So it's not exactly low rank, but it's, the hope is that it's approximately low rank.
Got it. Okay.
But yeah, that's it. I mean, for stochastic control, so some simple stochastic control problems, I think it's more clear to show that it is low rank. But yeah, for the OpenAI Gym ones, it's a little bit more empirically plotting the spectrum and looking at its decay.
Thanks.
Just another question, please. So you assume this kind of work where you start at the terminal point and then you do backwards induction, and so the errors sort of percolate backwards. Mm-hmm. Is it the situation that you would always encounter this kind of doubly exponential growth, no matter how you did your recursions, even if you tried to do something starting from the middle?
That's a great question. I mean, so I will. So there are definitely some things that break this example. I mean, which you might guess. So in particular, I guess this double exponential growth is for policy evaluation. In fact, if I were to do the same, take our example and do like policy optimization, so actually just take a max, it won't grow doubly exponentially. So there is, I think I think it is a question to know, like, how far reaching could this example go? This was one example in which I guess it fits the algorithm that was also used in this previous paper. But you'd be curious to know if this could be a stronger statement to be made here.
Thank you.
Yeah. All right. So given the example, we need to revisit the low rank. Revisit the assumptions, or I suggest that we probably want to revisit assumptions. So minimally, we started with this assumption that the optimal Q function is low rank, and the challenge is that we don't actually sample from the optimal Q function. And this is my only assumption. It doesn't give any guarantees on the Q function for other non-optimal policies. And so what we're going to do is show positive results under additional assumptions. In particular, we will show positive results under three settings. The first setting is that in addition to the optimal Q function being low rank, we also use the fact that there's a suboptimality gap that is bounded away from 0, and the sample complexity will depend on the suboptimality gap. The second setting is one where not only the optimal policy has low rank Q function, but all epsilon-optimal policies have low rank Q function. And the third setting is the most strongest. It's the setting where we're going to assume that the transition kernels and the reward function are in fact low rank. And so these are three settings in which we can show this gain in sample complexity to scale only linearly with S plus A, and we can show just a polynomial dependence on the horizon H. Okay, so next I'm just gonna I guess describe the three assumptions a little bit in more detail. The first assumption that the first setting is that there is a suboptimality gap, delta min, which is bounded away from 0. How the suboptimality gap is defined is with respect to these delta H. So this delta H at state X and action A is the difference between the optimal value function at step X and the value of the optimal Q function evaluated at step X and action A. So it's just the how much suboptimal you are just from deviating from the optimal policy at this one step H, taking this action. And the delta min is just the minimum of these suboptimality gaps over all steps H and all states X, all actions A. And so the results here will depend on delta min. I guess one comment is that for the tabular setting, when you have finite states and finite action, the suboptimality gap is always non-zero. But the question would be whether when the size of the states in action space grows, does this suboptimality gap have a dependence on that size of the states and actions? And that would then factor into the final bound. The second assumption that we're assuming is that the near optimal policies are low rank. In particular, for all epsilon-optimal policies, their rank is bounded above by d epsilon. And so, of course, the choice of epsilon will affect the kind of bound on the rank d. The sample complexity, the cost for finding epsilon-optimal policy will have a dependence on this d epsilon. But the stronger, I guess, why this assumption is stronger than the first one is that, in addition to just the optimal policy being low rank, it also imposes that near optimal policies are also low rank. The third assumption is the strongest one, and to explain it, I'm going to first, I guess, introduce this visualization. You can visualize the reward function as the matrix here, and you can visualize the transition kernel by a third order tensor. And so we're going to be imposing rank with respect to a particular tensor rank. And so in the certain assumption, we're going to assume that the reward function viewed as a matrix is low rank, and that the transition kernel has low Tucker rank. In fact, we can actually relax this third condition. All we need is that the transition kernel has low Tucker rank either along the states, the originating state, or along the action that's taken. We do not require, and it's either or. If it's the transition kernel is low rank along either of these modes, then that's actually sufficient for us. We do not assume low rank along the destination states. So to give you some intuition for why this where this assumption comes from, turns out that if you assume the reward function is low rank, then transition kernel has this type of low rank structure. It does imply that the Q function is low rank for all policies pi. And additionally, it implies an even stronger statement that the result of value iteration for any value estimate v hat is low rank. And to visualize this, you can see that the Q function, or the result of value iteration, the estimate of the Q function using value iteration, is equal to the reward matrix R plus a weighted sum of the slices of the transition kernel tensor along the third mode where the weights are with respect to this estimate v hat. So maybe just to explain it one more time, if I visualize this tensor and I take slices of the tensor along the mode corresponding to the destination states, I'm just taking summing up these slices of these matrices corresponding to the slices of the tensor, and I'm summing them up according to a weight, and the weight that's given it is the estimate from the value function. So now you can see from this picture that if we had the condition that every slice of this tensor was low rank and furthermore shared either a row space or a column space, then when I sum in along the destination states in this way, according to weighted by any vector here, the corresponding matrix is going to be low rank. And that's exactly the kind of low Tucker rank that we need here. That's represented by this assumption. Okay. Any questions about assumptions? Maybe looks like there were questions in the chat, but maybe they were answered. Okay. So I did want to take a short detour. Oh,
Christina?
sorry, Dave. Yeah, go ahead, Dave.
So a quick question, like, how would we think about what problems would have this structure? Like, is there kind of a concept like this kind of problem would the Q function would be low rank?
Yeah, I mean, that's a great question. I mean, I think the easiest example, I think the most intuitive one is one where, so any problem where the underlying model is actually continuous and you arrive and you get to the MDP by a discretization, that would, I mean, I would argue that actually has low rank structure. The reason being, I should think of this Q function, like what does low rank mean? It means that the kind of this Q function, I'm looking at the rank and how it scales with S and A. But if S and A are arising from a discretization, they're kind of artificial. And so S and A, the size of the discretization doesn't really, shouldn't really affect the inherent complexity of the behavior of the system. And in that sense, there should be a kind of a rank that's determined by the inherent behavior of the continuous system. that would then be preserved when you discretize it. So I think the cleanest example is from a discretization. I think when you have a large state and action spaces that are not, that are actually tabular setting, but they're very, very large, such that you might believe they could be represented by a continuous model. That might be for something like, let's say your states and actions, like you say actions course, let's say in an inventory model where you have lots of products, and maybe why the state and action space is large is related to this large set of products. Even though these are distinct products, you could believe that these products kind of could be approximated as if they're sampled from a distribution, a population of products, and that the complexity would depend on that kind of population version of the model. Does that make sense? Yeah. Okay, so I did want to take a short detour to a different model just because it's one that's easy to confuse. So another model that's has recently been studied in RL theory is used for linear function approximation, assumes a very different type of assumption. One assumption they assume is that the optimal Q function is linearly realizable. That means that the Q function can be written as the inner product between a weight vector theta, which is d-dimensional, and this feature mapping phi. The feature mapping phi is a function that maps from a state action pair to a d-dimensional vector. And so you can visualize this feature mapping phi as a tensor. And this weight theta is taking an average along the direction here that's dimension d. The other type of assumption that's also commonly used is called linear MDP. Is also referred. It also is referred to as low rank MDP. So that's a little bit confusing because we're also looking at low rank assumptions. I'll note that it's actually a slightly different type of low rank. The linear MDP setting assumes that the reward function is linearly realizable. Additionally, that the transition kernel can be decomposed according to a function mu of the destination state x prime and the feature mapping phi on your originating state and the action that was taken. The best way to visualize it is that it assumes this tensor is can be written as this product between the S by D matrix that it comes from mu. It's a representation of the destination states and this feature mapping phi. And so if we look at this and compare it to the assumptions that we had, this is assuming low Tucker rank, but along the mode corresponding to the destination states. And it's very, it's distinct, particularly it's distinct from the assumption that we need, which is low rank with respect to the originating state or the action. Sorry, Dave, did you have a question?
Yeah, so it looked like your bounds were like stated for sample complexity.
Yeah.
Is this also for computational complexity?
Yeah, computational is a very simple algorithm.
Okay.
Yeah. So, all right. So I guess the comment I want to make is that this kind of assumption does not actually imply the Q function is low rank when you view it as a matrix. So if I look at this here, this feature mapping phi does not need to have any structure with respect to the relationship between X and A, which is particularly the kind of structure that we're going to consider when we say low rank here. So this does not imply the Q function is low rank. And oftentimes this feature mapping phi is assumed to be known. So this feature mapping phi, if you look at this picture here, it's actually the most complex part of the model. It's the tensor portion. So in this sequence of works, oftentimes phi is assumed to be known. And so the unknown portion ends up being reduced to something very, very small. And so the goal often in this set of works is to actually remove dependence on the size of the states in action space entirely. So it's also, and that's another very different aspect. And when the feature mapping is unknown, but it is, but a given small function class that it lies within, there are exponential time or coefficient algorithms, but that can improve sample complexity. But yeah, but again, this is a very different model. So all right, so so recall the goal of our, the presentation today is to tell you about these three different settings and how we can achieve the efficient sample complexity under them. And what we'll present is a new algorithm we call low rank Monte Carlo policy iteration that will achieve this S+A gain for all three settings. And additionally, we'll provide a new analysis for an existing algorithm which we refer to as low rank empirical value iteration. And this will be able to show, the sample efficient bounds for the strongest setting when the transition kernels and rewards are also low rank. So let me tell you about the algorithm. It's actually very simple. It's exactly what we alluded to earlier. You take empirical dynamic programming and then you make it low rank by, so in particular, this step, when you're computing Q hat using empirical dynamic programming, you only compute it for a subset of state action pairs, XA, within this subset of state action pairs omega. And then you use matrix completion to estimate the Q function for all state action pairs. So this matrix completion here is this black, here I've depicted as just a black box that takes as input the estimates Q hat from empirical dynamic programming over the subset of entries omega and outputs an estimate for all state action pairs. And that's the only part that's really different about the algorithm. Otherwise, it's just empirical dynamic programming. And we're going to show two variations of the algorithm. Again, the first one is actually an existing algorithm that I referred to before in Shaw et al. And also in the paper Young et al. It's a low rank empirical value iteration. It takes how it computes this Q hat is using the empirical value iteration, this one-step update. And we're going to sample NH samples from the transition kernel, a one-step transition for every state action pair within this sample set omega. The other algorithm is called low-rank Monte Carlo policy iteration. That's what we are also introducing. And in this one, the only difference is that we're going to compute Q hat using a different empirical dynamic programming procedure, where we're going to actually sample full trajectory rollouts given this approximate policy. So in particular, this Monte Carlo policy iteration is tracking the approximate policy. Given an approximate policy, it computes Q hat by sampling an entire trajectory rollout using that approximate policy for each state action pair within this sample set omega. And so it's just using the original definition of the Q function to approximate, and again, replacing this expectation with empirical samples. And the one thing we need to specify is how do we actually determine the set of samples that we're using empirical dynamic programming for, and what is the matrix completion algorithm going to be? So we'll take a detour to matrix estimation. And we'll kind of show two algorithms. The first option is an algorithm that is proposed in Shaw et al.'s work. And in particular, the main, I guess what's going to determine whether an algorithm is going to work for us or not is that whether we're able to obtain entry-wise bounds. So I guess I did want to point out that few algorithms in matrix estimation literature actually admit entry-wise bounds. And so that's definitely an interesting area as well, independently. So this algorithm that was proposed in Shaw et al.'s work chooses this sample set omega according to this pattern here, where it chooses a selection of states they call anchor states, S sharp, and a selection of actions called anchor actions, A sharp, and it samples all the across this row, the entire row corresponding to anchor states and the entire column corresponding to anchor actions. And it computes the estimate of the matrix according to this formula here, where this first term is the vector corresponding to the state X that intersects with all the anchor actions. This vector here is the vector corresponding to action A that intersects with all the anchor states. And this matrix in the middle is this yellow matrix here. And you take the pseudo inverse of this matrix. And if you, so if you plug in the true, like if I did not have estimation, if I had the true values, you can plug this in. And if you choose a large enough S sharp and A sharp, you can see that this is in fact exact. What we additionally assume, what we are additionally able to show in our work is that if you assume that this matrix is incoherent and the condition number is bounded, then it is in fact sufficient to just randomly sample the anchor states and actions. So the nice thing about this algorithm is they have like a very explicit form, and so you can get very explicit error guarantees. The other algorithm that we're going to also suggest is to just use the classical least squares with nuclear norm minimization. And under incoherence, bounded condition number, uniform sampling, and sub-Gaussian mean zero noise, Chen et al. Have actually provided asymptotic entry-wise error bounds. So because of the existence of entry-wise error bounds here, you can actually also use this algorithm to get very similar results as we showed today. So you put all the pieces together and you get the full algorithm. So the low-rank Monte Carlo policy iteration, again, just uses backward recursion starting from the end of the horizon, samples random anchor states and anchor actions, uses the Monte Carlo policy evaluation to estimate the Q function for the sets of state and actions within this special set, and then uses this matrix completion algorithm to estimate the Q function for all the remaining entries. And then, given this estimate of the Q function, you estimate the value function and the optimal policy, and you recurse backwards. The low-rank empirical value iteration is the same, almost exactly the same, except for you replace the middle part with the empirical valuation instead of the Monte Carlo rollouts. Any questions about the algorithm? Okay. Oh, yes, Dave.
Real quick, so could you just summarize, so the key difference between the previous SHA algorithm and your algorithm is what exactly?
It's only that the previous SHA algorithm uses value iteration here, where you're updating based on the previous estimate for the value function. And our algorithm is using full rollouts of the trajectory. So it's the samples here, the cost of the samples for like a single step is going to be H times more, because instead of sampling only one step transitions to compute E hat, you're actually sampling the entire rollout of the policy to the end of the horizon. That's the one difference.
Okay.
Yeah. Turns out it's a significant one for the analysis, and I'll hopefully show you exactly why. All right, so we have kind of three parts of the I guess theoretical guarantees. Again, corresponding to the three different settings that we introduced. The first setting is that when your optimal policy is Q star, I should also highlight, and you have a suboptimality gap. And under this suboptimality gap, we get a sample complexity that scales with 1 over the suboptimality gap squared, and we do get, under this setting, you actually get the optimal policy. So this is the sample complexity to get the optimal policy. And the second setting is when you have the assumption that all epsilon-optimal policies are low rank. Then you have a dependence to get the epsilon-optimal policy, the sample complexity 1 over epsilon squared. So between, I guess, the first two, and both of these, I should have highlighted that these are both theoretical guarantees on the Monte Carlo policy iteration variant of the algorithm. So the algorithm that we're going to propose. Let me get, I just want to make a comment that this result does extend to continuous space MDPs under Lipschitzness. Yes, yeah.
You had the lower bound on the complexity earlier, right? The negative result.
Yes.
But that's for value iteration. But
Yes.
here you're using like a Monte Carlo approach. So the value iteration lower bound is not applicable here, right? In other words, there the epsilon thing is getting accumulated. Here you're not even using the value functions. You're just rolling out. So that's not applicable here. Right?
Exactly. So that is in fact very important. And that's actually why, so as Eva mentioned, because the Monte Carlo policy iteration doesn't accumulate the value, the error in V hat, it only it only gets the error that is in pi hat. Then you can see that all of our assumptions here are going to be on the pi hat essentially. And so this condition that the epsilon optimal policy pi is low rank is used to enforce that this pi hats that we obtain in Monte Carlo policy iteration, that they correspond to Q pi's that are low rank.
So a follow-up question then.
Yes.
So now that these two are different settings, I can go back to the original thing. And then if I say that I don't want to make any of these three assumptions, maybe it's conceivable that it doesn't have this double exponential blow up anymore, right?
Well, so the first assumption, this first assumption is actually pretty weak in that we're only assuming the optimal policy is low rank. The only additional assumption we had here is that there's a suboptimality gap. So where this assumption is being used is to make sure that when you use policy iteration backwards, that this pi hat, you want to maintain that pi hat is always the optimal policy.
Right.
Because once you deviate away, then you don't have low rank anymore.
I see. Got it. Thanks.
Okay. So yeah, so I guess we're just gonna dive into those comments a little bit more. The proof sketch really is 3 pieces. So first of all, you show that assuming the incoherence is sufficient to sample these anchor states and actions at random. The second step is to show that assuming this, also additionally using the boundary condition number, that the amplification of the error from the matrix estimation is directly bounded by this quantity. So if all of my estimates from the empirical dynamic programming part of it was bounded by eta, that the matrix estimation part of it amplifies it by the condition number squared times the size of the state, the anchor states, and the size of the anchor actions. The critical part to observe here is that this, if you have bounded condition number, and you should think of the anchor states and actions being scaling, they scale as the rank. So it's kind of condition number squared times rank squared, but you're just amplifying the error by something that's assumed to be a constant, and that's the critical piece. And then the third piece is actually straightforward. You just show that the Monte Carlo policy iteration does in fact maintain either an optimal policy or a near optimal policy. So the first step of it to show the kind of that random sampling of anchor states and actions is sufficient. First of all, I want to, I guess, formally introduce here what's the definition of incoherence. So the matrix Q is incoherent if the maximum L2 norm of the row of these, so here I have depicted here that the singular value decomposition of Q is U sigma V transpose. Incoherence is a property of the singular vectors, U and V. And in particular, it's stated as the maximum L2 norm of the rows of this matrix U are bounded by square root the rank D over the size S. And similarly for the column row space. But the intuition that you just need to know is that the idea is that the mass is kind of spread uniformly in some nice way across all the rows and spread uniformly in some nice way across all the columns. And so, so if you let U tilde and V tilde represent the portion of the singular vector matrix as limited to our anchor states and anchor actions, the key piece is just to show using matrix Bernstein that that these the columns of this U tilde and V tilde, when you restrict it to the anchor states and anchor actions, are in fact nearly orthogonal. And this nearly orthogonal property then subsequently implies that this anchor submatrix that's used in the algorithm is rank D, and that it captures all components of this equivalent that are important. The second step is to analyze the matrix estimation algorithm itself. And so recall that the matrix estimation algorithm had this particular form. What you just show that the error can be written as kind of at least the leading term in the error can be written as the operator norm of the kind of the difference between your estimate Q hat and the true Q function of your policy pi hat. Or the difference between the pseudo inverse of these two core matrices. These matrices correspond to this yellow matrix here, and the Frobenius norm of the inner product between this green vector and this brown vector here. And so you can directly bound both of these terms, and use the fact that use the bounded condition number to show that this QH infinity over the smallest singular value of this anchor matrix is bounded. And I guess here I want to make the side comment that if you instead use the nuclear norm penalize these squares, you could instead use the asymptotic entry-wise bounds from Chen et al.'s work. And
may I ask a question?
Oh yes, go ahead. Yeah.
Sorry for interrupting.
Yeah.
So very interesting. So my question is, there is this assumption that the all epsilon approximate policies should have low rank Q, right?
Yeah.
So is it okay if they have an approximately low rank Q?
We do have some results for approximately low rank, but the approximation error will also accumulate with the horizon. Maybe not exponentially though, but linear with the horizon. So there is an approximate rank, variant of it. I guess the one assumption you'll need is that how much approximate low rank it is as the horizon gets large should get small with the horizon in order to make sure that it kind of doesn't dominate.
Got it. I mean, for somebody who wants to implement an algorithm, like, do you think they could use your thing even though it's not exactly low rank for approximate optimal policy?
I mean, I do. I think that. I think that so we have not yet done empirical validation for this, but there has been empirical validation on the low rank empirical value iteration method, and it does seem that there is value in practice even when it's not exactly low rank. But
sounds good. Sounds good. Thank you.
Okay, and the last step is fairly straightforward. It's the induction step to show that well, because if the entry-wise bounds of the matrix of estimating Q hat is bounded by this quantity that came from the last step, and by Hufting's this eta, it scales as 1 over square root n, which is the number of samples. You just choose the number of samples so that this kind of how much you're accumulating the error in the optimal your estimated policy is kind of bounded. So if you under the suboptimality gap condition, you want this thing to be bounded by delta min, and under the near optimal policies condition, you want this quantity to be bounded by epsilon of h. Okay, so the other theory, the other result we have is that is for empirical value iteration. So under the assumption that this matrix here is low rank, and this matrix here being low rank is actually implied by the reward function being low rank and the transition kernel being low Tucker rank. And I guess the way you should visualize what is this matrix here, it's simply the one-step update using value iteration. So under the assumption that the one-step update from value iteration is low rank, then you can also show positive results for this low rank empirical value iteration algorithm. I mean, that's not true, and as you can guess, it's just because the empirical value iteration, the output of the algorithm at each step is in particular this expression here, and this expression needs to be low rank in order for the matrix estimation algorithms to make sense. So there's you kind of save one factor of the horizon, because instead of sampling the entire trajectory rollouts, you only sample one single step transition. So that's the gain for empirical value iteration. But also I want to point out our current theory only gives you an epsilon-optimal Q function. And given an epsilon-optimal Q function, you can find an epsilon-H optimal policy. But we believe that you can actually use techniques from Sidford et al.'s paper to actually reduce this factor of H here. And I guess I want to also comment that these results do extend to continuous space MDPs, also under Lipschitzness, and they also extend to discounted infinite horizon MDPs and also approximately low rank settings. And the proof is basically exactly the same, except for instead of analyzing this Q function estimate away from Q pi, you're analyzing this estimate Q deviation from this result from the value iteration, which is again low rank by the stronger assumptions. So to loop back to our negative example, kind of our negative example was one in which the transition kernel was not low rank, but so we believe that potentially the empirical promise in the example, the empirical success of that have been shown for this result, we kind of guessed that it could be because of the stronger conditions of low rank transition kernel in addition to low rank Q star. Okay, so this is the same. And so I guess in summary, we kind of showed under 3 different settings of low rank structure that you can actually reduce the sample complexity dependence on S times A to only S plus A and not have to incur this very costly horizon dependence. So we're able to get polynomial horizon dependence. And we showed a new algorithm that's based off of a Monte Carlo policy iteration, as well as a new analysis for the empirical valuation. So a couple open questions are whether we can actually relax the generative model assumptions, whether we can relax the low rank assumptions on infrequently visited states. So it seems kind of it seems unnecessary that we need this structure everywhere, even if the optimal policy doesn't visit everywhere. Can we actually show more explicit and stronger lower bounds to actually prove low rank RL is harder than classical low rank estimation? And can we actually get low regret algorithms for an online RL setting? So these are all very interesting open questions. And finally, I just wanted to loop back to the broader research goal of designing algorithms that they can provably and efficiently exploit structure. So today I talked about this work on low rank structure, and the preprint is available on my website. I also want to give a plug for a software package OR suite that our group has been developing, where we have implemented many operational problems and in such a way where you can actually use to benchmark RL algorithms. And along with this package, we have included domain heuristics to benchmark against and multiple metrics that you can also compare with. And so we're also hopeful that this OR suite package can hopefully catalyze more research in this direction for looking at reinforcement learning algorithms that actually can tune more to problem-specific structure. Thanks, I'm happy to take questions.
So one question about the previous slide. When you showed your bounds, it felt like your conditions were strictly getting weaker, but your bounds are somewhat incomparable.
That's yeah. I mean, so the first two, I think it's because of the suboptimality gap. You get this delta rather than epsilon, and the reason for this extra dependence on the horizon is because you actually get the optimal policy. The proof is that you maintain the optimal policy, so that you don't have this issue that you need to like make sure your error doesn't accumulate too much. So making sure that to get an epsilon optimal policy, you need to make sure at each step you only incur epsilon over h additional error, and so the epsilon over h part gets this extra h. And then between the second and third one, the drop from h6 to h5 is because the value iteration only gets like, samples an h factor less of samples with this as opposed to the full trajectory.
Right. So then, okay, the first two then make sense. So the question about the value iteration, like intuitively, is the gain that you're getting that value iteration has lower variance compared to Monte Carlo, or do you have a sense of where you're getting the gain? Value iteration? Well,
I mean, I guess my answer was more simpler maybe than that, but I think you're right that maybe there may be a question with respect to bias and variance. So here I would say that the gain really is just that algorithmically, like the number of samples nh that I need to sample is still the same, but the cost of each sample in policy iteration is I have to sample to the end of the horizon, so I count it like it's costly by a factor of h, but the number of samples I need to take is still the same. And the reason, like what you gain in an analysis for Monte Carlo policy iteration is that you don't have because you're analyzing your deviation away from like this Q function for this policy pi hat, you get like mean zero samples from this policy pi hat, and I guess you don't have that like under the in value iteration. This when you're iterating on this v hat, that corresponding function might not correspond to any actual Q function, but that's why you need the stronger assumption there. And so yeah, I'm not sure, is that enough of an answer?
No, that makes sense.
So sorry, just separately, I'm curious. So getting to polynomial in the horizon length is great, right? So that's a huge step forward, but I still live in fear of h to the power of 4. Could you say something about how tight those things might be?
Yeah, that's a good question. I mean, well, first of all, actually there is a lower bound where h to the cube, so maybe we're losing, so h to the power of 4, maybe we're losing by 1 factor of h. Where we're losing it, we're not really sure. We did not optimize it a lot, so I think it's definitely a worthy question to look into. Yeah, there were a lot of but there's a lot of technique. I think there we would probably want to look at the RL literature for other techniques people have used to try to reduce the horizon dependence and see if we can also port it over to our analysis.
I had a quick question. So if it's low rank, you kind of, I guess you need to firstly, well, if it's not low rank, what's the system by which you decide what rank to work with? Would it be like, I think you mentioned it earlier, you could maybe do it for the full thing and then do an eigenvalue, find the eigenvalues and look at the most significant of those. If it was that case and you ran like a low rank algorithm on it, am I correct that because your results are kind of entry wise and it'd be sort of like the worst entry wise approximation that gives you your error away from the true optimal? So, you kind of converge on something that's a good solution, but not the optimal one. And there's going to be a distance from that to the true optimal. Because that's what you do with linear function approximation in MDPs. You can sort of say you're going to get to some solution and then there's a distance from that. I was wondering how that kind of plays out here. I guess it would be okay. It play out quite well because you're working with things on the entries individually.
Yeah. So I mean, you're right that like the way the error goes is indeed just by simply using the entry-wise error bounds. And so the extension we have to the approximately low rank setting is also kind of an entry-wise type of approximate low rank. So it's like low rank plus an entry-wise deviation. And so I mean, because we only need the entry-wise kind of bound, it does allow, I mean, that's what allows our results to kind of extend in some way. The one thing that I had commented was that the error does still accumulate like linearly in the horizon though. So any bias you have in the, that's due to the approximately low rank part of it, that part you can never get rid of it and just kind of accumulate it linearly through the horizon. Versus the other part of it, you can just take more samples and reduce, right? And that's actually exactly what, so the alternate analysis you could use for this method, which is the one used in Shaw et al., is to instead look at bounding the deviation between the estimate of the Q function and the optimal Q function itself.
Yeah.
But when you don't actually sample from the optimal Q function, you have a piece of it which is due to the variance and a piece of it which is due to the bias. And it's because they have to additionally incur this this cost in the bias that amplifies that results in their condition that meeting bounded horizon. But that is an alternate analysis you could use. Yeah.
Okay, great. Thanks. Enjoyed your talk.
Oh, and so that was Rashi gave a good suggestion that definitely, because we also used Hufting, it was loose, so maybe using Bernstein could save the factor of H. Yeah. Dave, did you have a question?
Yeah, so I guess either using standard methods or something from your analysis directly, is there a clean, maybe implicit in what you've done, way to interpolate between S plus A and S times A as the rank gets larger? Or is it more like we're using black box things that need the rank to kind of be low, because then you get a kind of logarithmic asymptotic sum?
Oh, we can interpolate. So you can think this D actually can, depend on S as well. So this D is the rank is. Unfortunately, I think something maybe loose is it's D to the fifth, and ideally you really want to get down to the linear in D, but that's also.
Okay, so I see. So D here is the rank.
Yeah. I mean, D is the rank.
I have a question related to my earlier one. So suppose you're in an environment where the transition kernels are approximately low rank in some appropriate sense, right? So So would that imply some good low rank properties of the Q for the optimal policy or approximately optimal policy?
Sorry, say again. You said if what was the low rank? If the.
So let's say two things, right? One is that the transition kernels have some approximate low rank structure.
Oh, yeah.
And maybe the reward functions are low rank, right? So I'm just trying to sort of stress test what is required for the Q to be even approximately low rank, basically.
Oh, okay. Okay, so let me actually flip to that slide. I think this picture is probably the most helpful one. Okay, it's this picture. Okay, not this picture. Sorry, this picture. So I guess the way you should think about why what makes the Q function being low rank, it is the Q function is a result of this kind of operation, and if each one of these slices are approximately low rank, the amount of approximate low rank that you incur in Q is going to relate to the weight V along with the approximate rank, low rankness of each of the slices. So I guess you will get, so if this is kind of, in particular, the type of low rank that you would want for here would be, I mean, we have our results in terms of a total variation distance, approximate low rank, and that's because, you know, total variation distance, you're kind of summing over all the states. And here, how you get this Q is by summing over the states that you transition to. That's the kind of, I guess this is how you would incur like low rank, approximately low rank from T, imposing approximately low rank on Q, was you accumulate it across the slices here, weighted by the value function.
The value function will not create trouble. There won't be an accumulation of the sort of errors and low rankness of the transition kernel across time.
Oh no, there isn't. And so that's actually that's the beauty, is that like how like this Q function, what's the dependence on the future dynamics? It's all captured only by v hat h plus 1.
What was
so
that object?
Oh, so this is like the future. So the value for like for the agent at starting from step h plus 1 at state x h plus 1 to the end of the horizon, and you're weighting this to this expectation with respect to this x h plus 1. And so this value function, again, it's bounded because we're assuming bounded rewards, and this is the only kind of thing that kind of couples from step to step, because RH and TH are only, you know, just for this one step. So there's the nice thing actually is it doesn't really accumulate.
Okay, that's nice. Thank you.
So Christina?
Yeah.
Maybe this is like related to what Sid had asked before, but like, so it's you know, it's very intuitive and it makes sense that I guess optimal policy, you can have the optimal policy, but the Q value, you're never gonna have the optimal Q value. And so that there's a gap there. And I'm wondering, like, from Devavrat's, from the previous approach, is there any way in which that is scaling preferably, or is it really like you really want to go with the policy in this setting if you want it with high probability result, and there's not really any other way in which that approach is saving somehow?
So I think that, okay, so the thing that's kind of hiding is that these things do depend on the assumptions, right? Like with the different analyses are not over the same assumptions. So in particular, like when you can get the like make sure that you get the optimal policy, it is dependent on the suboptimality gap. When the suboptimality gap delta is like super small, maybe you like don't mind incurring the extra factors in H. So first of all, like if this first assumption on suboptimality gap is actually very weak, you know, maybe this extra H factors that you incur is actually preferable. And then between the like these two settings, when you're not relying on this delta min, you're just tracking near optimal, then I mean, I feel that the gain, like it is better to use the empirical valuation, the algorithm from Devrat's paper. Likely the only caveat in the analysis is that you somehow have to show that getting a near optimal policy, a near optimal value function gets a near optimal policy, and you would probably want to use the kind of techniques that were developed in this paper for the tabular setting, which actually did involve changing the algorithm slightly. So you would probably need to actually change the algorithm also slightly to make sure that you can actually get an epsilon optimal policy, but still not incur any extra factors in H. So, I mean, I think that probably, like in practice, I would, if you think that the stronger assumptions hold, then I would still go with this value iteration. Now, I guess maybe the one more question is that when, I don't know if you were wondering, if the stronger assumption did not hold, can I still get a good analysis for value iteration? If that's what you're wondering? And
not really. I was just wondering, and I guess this speaks to a meta question also, just like, again, it's a nice and intuitive insight that for some natural settings, in this case, you look at low rank, the definitive binary yes, no that comes with knowing your policy is really on the money can kind of save you in the analysis significantly. One could also ask, are there other settings where, maybe people have written a lot of papers on value iteration, et cetera, where they didn't realize that if you just did the analysis with the definitive yes, no of having the optimal policy, you would similarly get good things. It seems like a meta.
I see. That's a great point. I mean, I do think, so I do think that's the right insight from here. And maybe I guess the other comment, it's not that you can't analyze value iteration, but the problem is that because of this non-linearity in the estimator, if you didn't have that Q pi is like low rank, the way that the analysis goes for value iteration for a Devereaux algorithm, or a Devereaux analysis is you kind of have a bias piece of it, which is like you're getting samples from a matrix, a low rank matrix plus a bias. So you're not, it's actually much harder because it's as if you have a low rank matrix and I'm getting samples that are actually not mean zero noise. They're bounded noise, but they're not mean zero. And dealing with the not mean zero noise is actually like what causes all the problem. So I think that is interesting, and I think definitely could be true that, and I think in the beginning we were really zooming in on understanding like what maybe it's like what the role of this non-linearity causes in the proof and how it makes things difficult. So maybe there are additional settings where there's nonlinear estimators and something like this might show up, and that'd be interesting.
But I guess like as a meta point, in some ways, it doesn't really matter that the error is accumulating in a complicated way here. It's more just like when you think about the optimal policy, with high probability, literally you have there's zero error in some sense, right? And so
exactly. Yes, that's true. That's true. That is true. Yeah. And I guess Ranshi asked about this difference between epsilon and the H24 to the H6 in the suboptimality gap to the epsilon depending about. So the reason for that was that when you're tracking how the error in the Monte Carlo policy iteration accumulates. When you have a suboptimality gap, you just need to make sure that this error kind of is bounded by something like delta min. That's independent of the horizon. But when you are getting a near optimal policy, you have to, because you're accumulating the error in an additive way across the horizon, you need to make sure that this error kind of is bounded by epsilon divided by h, and that's divided by h. This piece is what gives you the extra kind of h squared.
Thanks.
Yeah, and the square root here, I guess that. Yeah. Thanks.
One higher level question, this may be as much for like other people here. Like, do we know an example of MDP which isn't in this setting for which we actually know good, or we know how to get good policies? So what's an MDP which we know how to solve which actually doesn't fit in low rank? This version. For anyone, because then maybe alternate question, is it possible there's a lower bound, just that if an MDP is computationally solvable, it somehow is low rank in some appropriate sense?
Yeah, that's intriguing.
So in other words, have we just completely solved stochastic control and there's nothing left for us to do?
Well, the funny part is that I feel like most people ask whether, like, push me to motivate why low rank is realistic. But I think, I would be very interested to kind of understand more like where this assumption shows up or where it doesn't show up, and getting more intuition on that.
Now you've provoked Sid Banerjee. So, okay, I'll throw out to Christina and the crowd. So I assume it's intuitive what would be the case where the rank is 1 of the optimal Q function. Hopefully, can we pin down that? What does it mean when the Q function is rank 1?
I mean, Q function is 1 is not very interesting because then there's like there's an ordering of all the actions and all the states such that like uniformly across all states, this ordering of actions is preserved in terms of like the best action to the worst action. And
okay,
similarly, the
like a chain where no matter what action you do, you get a function of that action and then you transition totally randomly to the other states. Is that would be a rank 1 Q? Which would say, you have 10 states and then in every state, like the action gets you the same reward and then you jump totally randomly to a different state.
No, I think Christina said.
That's not an example of what you're saying. No.
You don't even need something as strong as that. You don't need that. You need that. Okay, so the confusing thing about the Q function is, right, it is a cumulative thing, right? Like depends on the full dynamics, right, to get what the Q function is. But and this assumption is on the Q function, and rank 1 means that I can order all the states, order all the actions such that the value I get, like, okay, so the first one would be no matter what state I'm in, the order of which action is better, which action is second best, third best is always exactly the same. Like, so this action uniformly dominates across all the states.
So fair enough. So then I'll throw it out. Is this
also the opposite?
Sid Banerjee, right?
What?
Or that sounds like an index, some kind of indexable property, I guess, right? Or is this?
Oh,
can we flesh it out? I mean, because on the one hand, it is formally clear what you mean when you say there has to be a fixed ranking, etc. But there still seems to be a gap as to what that precisely means, right? Like,
yeah, and I mean the state space, it would mean that like, yeah, there's also a ranking over the state space that this state is like more desirable to be in than the other state, no matter what action I took, or not exactly no matter. For a fixed action across that states. This is the ordering that.
And then I guess is there a case?
That's kind of a weirder state.
Can the Q function be the identity? Is there a trivial MDP where like the rank is obviously n because it just reduces to literally the identity?
Yeah, you can construct one where the Q function is identity. Yes.
So I guess there might be your answer, Sid Banerjee. I guess there's the identity MDP, which I assume we can solve, right? I don't know.
Identity MDP is actually kind of like
maybe it's
in some ways. Well, like no. So if you should think of the identity MDP under permutations, right? Like if I knew that for this state, there's exactly uniquely one best action. For a different state, it's a uniquely different best action. But then I look over all permutations of like actions, right? That's actually hard.
Yeah, that's sort of like a search problem in a S to the H. Like imagine your graph was S to the H, and like at each stage you needed to, there's one destination state you want to get at. That would be very hard. Like you have to always pick the right action.
I can believe that. I'll have to think about that. It's interesting.
That still leaves my part about those are hard MDPs, but those are also uninteresting MDPs. What's?
Well, and then this, okay, I mean, I guess this gets to the meta question too, of for all the definitions of rank out there, of course you can ask how they relate, right? And that's, I don't know.
Almost all the other definitions of rank out there, right, are really looking at, they look something more like these things. They're actually more oftentimes related to the decomposability. Like it looks more like these linear MDP type of assumption. And the reason why is like, this is kind of, this kind of structure is kind of governing how does the next state you transition to relate to the previous state and action you came from? And so the kind of rank that people have been looking at a lot is related to the Bellman operator, like ranks related to the action of the Bellman operator. And the action of the Bellman operator, right, is taking you from XA to X prime. And so most of the existing definitions of rank are really looking at understanding structure of how it changes your dependence across time of like X to X prime. And that's why it ends up being something that has a little bit more of this form versus this is a very different kind of low rank that actually is not, is completely not equivalent. Like, there are low rank in that setting doesn't imply low rank here doesn't imply low rank there. It's very different. So most of the rank with respect to that people have looked at for our theory now have to do with the Bellman operator, and that's like this relationship xa to x prime.
And I assume it's not like obvious that like take like a extremely simple inventory where an order up policy is optimal. I assume it's not obvious whether that's low rank or not, or is it? I mean, I have no idea. I guess it can be worked out. I mean,
happy to think about it. I mean, my intuition for low rank is that if you believe that there is a low dimensional representation that captures everything you need to know. So if you believe that you think you could take the representation, but you don't actually need to know the full exact state, you know, but rather there's some like, you know, you can, the easiest one being cluster. You can cluster the states and actions together in some way that like these states are similar, these states are similar or whatever. Then cluster, if you can cluster the low rank, but not just clustered, but if there's some like, you know, low dimensional features of the current state that you think are sufficient to capture. And that's again, not explicit, but I think that's intuition.
I think that's a great example because a lot of the cases where we know how to solve the system, they typically tend to have like a piecewise linear or a piecewise concave or piecewise convex value function. And the pieces are coming about because it's the same action for a set of states which are optimal. So it's like you go up to a certain point and then like there's a threshold policy or something of that sort.
Wait, does that lead to low rank or not? Are we?
That is low rank because of
you have block constant.
So then in order, you're thinking as an order of policy would be low rank. Would it be a low rank Q function?
I feel like it should, but Christina, you should write a paper telling us what all the low rank problems are.
I mean, my sense is that the so general like queuing network control problem, right? I mean, you can use a back pressure policy, and if that was optimal, it would be low rank. But if it's not, then it's probably not in some obvious way low rank. So I think it's generally not low rank. It's just that okay, we are not even shooting for that level of fine-grained optimality yet, and so we are happy with what we're doing so far.
I feel like sometimes the complaint that we get is that, well, you go from S times A to S plus A, but you still incur like maybe linear and S plus A is still like too costly. So like the kind of settings that you would like if S times A is too costly, you want to be in a setting where S times A is too costly, but S plus A is still like you're willing to incur. If you can't even incur S plus A, right, then you just have to, I think you have to make some even more stronger assumption. Like the feature existent, you know, knowledge of features and that like solves everything for you or whatever.
Yeah. That's another good point. Actually, S plus A is large in these problems. So because A is large and S is large. So yeah.
This was fun. Yeah. I think we drove away everyone else. Sorry.
Thanks, Christina.
All right. I'll actually stop the recording and let's send Christina again. Thank you.
Thank you. Thanks. I really enjoyed it. Great.
Bye.